Okay, for this particular set of lab exercises, okay, and this will be the final set, and this will be in reference to eigenvalues and eigenvectors, and just taking from what we had among our earlier book exercises from chapter 5. Like in the case of number 10, we were looking at determining the eigenvalues and eigenvectors of the square matrix, which consisted of the columns 2, 4, and 3, 1 in the elements. And now when we looked at the determinant of a minus lambda I, okay, we had a characteristic equation which developed into lambda squared minus 3 times lambda minus 10 is equal to 0. And factoring, okay, we ended up with the eigenvalues at -2 and 5. Okay, so the eigenvalues, okay, for this square matrix we have at -2 and 5. And in developing the eigenvectors, and again we had a minus lambda I quantity times x is equal to 0. And for lambda equal to -2, okay, once we had applied in the matrix that we augmented and filling in -2 for lambda, okay, we had for the general solution, we had that x of 1 is equal to -3/4 of x of 2, and x of 2 is free. And we had for the corresponding eigenvector, okay, we had -3/4 and 1. So we have for lambda equal to -2, the corresponding eigenvector we have at -3/4 and 1. Now, as for what we have for the other eigenvalue of 5, what we had here and applying 5 for lambda, okay, we had, again, running it through the mill once again, we have for lambda equal to 5, okay, again, we have for the reduced echelon form of the augmented matrix, okay, it turned out that for the corresponding eigenvector, okay, this ended up at 1 and 1. And you can see how this is going to appear in what we have for maple. Okay, and again, do not forget to include your opening statement, which we have to be with linear algebra. And now, just in the case of what we have with the first matrix, just to get this on display. Okay, so again, we have 2 and 4, 3 and 1. And what I will do here, okay, is that we have in copying, okay, so looking for the eigenvalues, okay, I have open parenthesis and close parenthesis, okay, and return. And we have the eigenvalues at 5 and -2. And just now in the case of the eigenvectors, again, still dealing with same matrix. Okay, so this is what we have here. And what we have, again, when we had the eigenvalue at -2, okay, the eigenvector we had at -3/4 and 1. And whenever the eigenvalue was at 5, the corresponding eigenvector was at 1 and 1. All right, now, and let's say that for what we have for the case in number 13, okay, so we have another square matrix, and in this one, okay, so we have, okay, so you have 2, 1, -1, 2, 3, -2, and -1, -1, and 2. And it was given that the eigenvalues would be 5 and 1. And in the case of the eigenvalue 5, okay, now working the problems out by hand and using the augmented matrix, okay, we had the general solution for x was x of 2 times the vector -1, -1, and 1. And this vector, okay, is the eigenvector which we have as the basis for the eigenvalue of 5. And in the case of the eigenvalue of 1, okay, from the augmented matrix, okay, we had two free variables from which we had two variable solutions collectively. Okay, we have x is equal to x of 2 times the vector negative 2, 1, 0, and we have plus x of 3 times the vector 1, 0, 1. And those vectors, again, would be the corresponding eigenvectors for the eigenvalue of 1. Okay, and if we were to see how this might appear in Maple, okay, so again, we had with first column, so we had 2, 1, negative 1. Next we have 2, 3, negative 2. Again, the last column we have negative 1, and 2. And once again, so I'm just going to copy this. And looking for the eigenvalues. Again, in the book problem, okay, they were provided. And to see if what the book gave, okay, reflects, okay, or yeah, is reflective of what is going to be on display in Maple. Okay, so you got 5, and if you notice you have 1s to appear, and that means that 1 is a repeating eigenvalue. Okay, but the distinct eigenvalues we have at 5 and 1. And in terms of the eigenvectors, again, don't forget the open parenthesis as well as closing out the parentheses. And so we have for the corresponding eigenvectors. Okay, so we have for 1 and 1. Okay, so we have one capacity, we have 1, 0, 1. And also we have negative 2, 1, 0. And we have with 5, we have negative 1, and 1. So we have consistency throughout.